study the important topic of the isolated DCDC converter. At the beginning of the lecture, a couple of months ago, we studied the DCDC converters, the not isolated ones. They are very important, interesting in many applications, but the isolated DCDC ones are also a large piece of a large bunch of the market and are important in a large number of applications. This lecture will be organized more or less like pointed out in this summary. We will briefly talk about the problem and advantages of the isolated conversions. Then we will present the flyback converter, the forward converter, and we will also study a bit the transformer. Again, you should know it, but we will see it in the view of SPICE implementation that is not so straightforward in many aspects. What do we know now regarding the conversion scheme when we need, in this case, a regulated DC voltage and we want to connect to the main grid that is AC voltage, 230 volt AC. The basic scheme that we can use is this one. We have the main grid here. Then we need a transformer. The transformer is needed because we need galvanic isolation. In principle, we could work without the transformer. You could use the rectifier, the bridge rectifier, or any other kind of rectifier here. At the output, you will have a not regulated DC voltage and quite high voltage DC. It's not important, however. And then you can use a DC-DC converter to obtain the regulated DC voltage that you need. A properly designed feedback checks and measures the DC voltage here and activates the DC-DC converter in order to get a regulated and controlled DC voltage here. This is the basic scheme that we studied with the addition of this transformer. As previously said, this transformer is needed for galvanic isolation, first of all. It's a security measure. The user, that is here, is never directly connected to the main grid with the huge power involved. And for safety reasons, this is very important and required from many regulations and rules. There is also another important aspect. The transformer has a turn ratio, and there is a ratio between this voltage and this AC voltage here. That is the first form of voltage conversion. You can decide if you want to amplify or reduce the voltage here. And this will reduce the stress on the DC-DC converter. As an example, it would be very difficult to get 1 volt regulated DC voltage at this output if here I will find a 300 volt unregulated DC. You could use a buck converter, but the duty cycle must be very small. And it is possible that this very small duty cycle is unfeasible with the power devices that you have. It's much better if you can get an initial reduction of this voltage from 320 volt AC to maybe 50 volts, and then use the DC-DC converter to get the final 1 volt regulated 1 volt. There is more freedom. Negative voltages are possible, for example, and again, more design freedom. There is a new design variable. In the initial design without the transformer, you can only change the duty cycle, more or less. The other components are more or less fixed. In this second case, you have another design variable, that is the transformer ratio and the duty cycle. This will simplify or allows more flexibility and maybe more efficiency, more security to the entire design. Disadvantages. First of all, weight, cost, and dimension of the converter system. This transformer is very big. The transformer can be very simply seen as the coupling of two inductors. The reactance of the inductors will be proportional to omega, and to the impedance will be proportional to the frequency and to the inductance of the transformer. But since the frequency, the omega, is very small, 50 Hz, 60 Hz, you need a very large inductance. In the end, these transformers are very big. We are talking about 10 centimeters, 20 centimeters cube, something like this. They are very big, they are expensive, their weight is large. Is there a solution? In this scheme, there is no solution, because the input frequency is 50 or 60 Hz. The only solution could be increasing the frequency at the input of the transformer in order to increase omega here and reduce the inductance. How is it possible to implement this scheme, this improved scheme? It is necessary to use an isolated DC-DC converter. This is why these isolated DC-DC converters are so important. In the new scheme, you have the AC main grid voltage directly connected to the rectifier, bridge rectifier in this case. Here you get a not regulated DC voltage, and you use an isolated DC-DC converter that in some way contains a transformer. There is always the feedback that will regulate the DC voltage here. Advantages, all the ones that have been mentioned before. Galvanic isolation still present. Design flexibility still present. Second design variable still present. And further, this transformer can be designed and can work at much higher frequency. We are talking about kilohertz, hundreds of kilohertz. And this means that this transformer can be very small and lightweight. This can also improve the conversion efficiency. Are there disadvantages? Maybe yes, maybe not. The design is more complex. Yes, it is true. This is more complex than a not isolated DC-DC converter, but the advantages are so big. Difficult cross-regulation. Sometimes these converters have more than one DC output. Maybe there is some complicated cross-regulation if you want to regulate more than once, but this is not a real disadvantage. This is a complication, let's say, that comes with an advantage, that is more DC regulated voltages at the output. In the end, the isolated DC-DC converters are a very good solution for this problem. And they are everywhere. There are isolated DC-DC converter in the power supply of this notebook, the box that we have, that in in recent years I've seen their dimensions reduced from a box like this to very small boxes. There are isolated DCDC converters in the supply voltage that we use for these smartphones. They are small like this. And there is a transformer inside. It's not possible to get that transformer at 50 Hz. They work at much higher frequency, and this is why they are so small and they are so light. This also means that they have very large efficiency. Otherwise, they would become hot and would melt. And this means that in this area there has been a large improvement in performances.